finished the, I think one of you emailed me in the morning, say that, the notes is not there, right?
Oh, Professor, I emailed you. Yeah.
Yeah, so let you know, I think I already posted there. So maybe there's something wrong, maybe a glitch or something. But
Okay.
if not, it's the same thing in the recording, right?
Right.
Yeah, so I have the old one here, right? This is the old one. Are you talking about this one, right? We finished counters, right? And we make up down counters, we made the modulo counters, and we learned about that, right? Now we're gonna move into what? Registers. Okay, look. Today's what? Okay. Anyway, so today we're gonna talk. Let me record. It's recording. So today we're gonna talk about registers, and then we're gonna talk about operations of rotate right, rotate left, shift left, shift right, logically, shift right, arithmetically. Okay. What is the definition of the register? The register is a set of flip-flops are sharing the same common clock. So sometimes they will tell you that my register is a 4-bit register. Sounds good? So when somebody tell you my register is 4-bit register, what does it mean? It means that I have a four flip-flops. Those 4 flip-flops are connected in a way that they are sharing the same what clock, and the outputs are 4-bit, or the location inside that register are 4-bit. It can store 4-bit of data. So normally D flip-flop is the right candidate to be used for building registers. So you guys know that the best candidate for the sequential elements to build counters is what? T flip-flop. What is the best candidate to build registers and memory? D flip-flop. Okay. So if I would like to build this, I can just say here is one of the flip-flop, here is one of the other flip-flop, and here is another flip-flop, and here is another flip-flop. So I have now 4-bit registers, but I didn't say how the input and output will be taken into consideration. So what is this actually called? It's called configuration. Configuration. Okay, in the configuration, we are expecting the following. We're expecting one register called SISO. One configuration of register is called SIPO. One of the other configuration is called PISO, and the last configuration is the PIPO. Okay, so how many configurations do we have? 4. What does those configuration actually is do? So if I would like to look to this example as a 4-bit register, but I didn't say what configuration is following. So what I'm gonna do, I would say that it is SISO. Okay. Let's see how this SISO will look like. It's basically, you already have here a flip-flop, 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 right? and this is what our clock. Now I would like to see on the implementation the configuration. So in that case, if I go ahead and just say it is SI, that means serial input. So SI, it's a serial input. In that case, my input is going to be from here in the D. So I have D here, I have D here, I have D here, I have D here, I have here Q, I have here Q, I have here Q, and I have here Q. Sounds good? So in that case, if I'm serial input, I'm expecting serial output. And how I'm gonna communicate, I'm gonna go like this. So what I have in front of me is what? Serial input, serial output, serial input, serial output, what? 4-bit register. Sounds good? Hello? Hello? Can you guys hear me?
Yeah, sounds good.
Yes.
So everybody's following me?
Yes.
Is there any question regarding this subject so far? The functionality of the configuration, how it's gonna work. Imagine that I have a chunk of data, and this chunk of data is like this: 1, 2, 3, 4. B0, B1, B2, B3, and each one is a single bit. So B0 is 1 bit, B1 is 1 bit, B2 is 1 bit, B3 is 1 bit. It can be 0 or 1, it doesn't matter, right? And I would like to operate it on this SISO configuration. So how it's gonna work? So basically, if you already have here a clock, source of the clock, right? So I have here 1, 2, 3, 4, 5, 6, 7, 8. Here's our 8 clocks. I'm operating in a positive edge, right? So here's 1, 2, 3, 4, 5, 6, 7. Okay, here is our clock. Now I have the SI input, right? So here is my SI input. Okay, so in the first positive edge of the clock, B0 is written. So it's written in which register, which flip-flop? If I call this D3, D2, D1, D0, so basically, that means D3 has B0N. That makes sense? Hello?
Yes.
So you guys following the example, right? Okay, now, if I would like to go into the second clock, what will happen? Second clock, SI will be pushing here what? B1. But then, in this second positive edge of the clock, who gonna be B0? He will be in D2, while D3 will have what? B1. Then, if I continue, so here is SI, then, what will happen? B2 will be in the D3, while B1 will be in the D2, and then this guy will be what? B0 in the D1. Then the fourth clock, while I'm pushing, so the B3, it will be in the D3, and then B2 is gonna be in the D2, and then B1 is gonna be in the D1, and then B0 it will be in D0. Do you guys agree? So in that case, I loaded the 4 bits. I loaded the 4 bits inside what? The register. Make sense? Now, there is no output, right? I haven't received any output yet. So what I need to mark here, it took 4 cycles to fill the resistor with the required data. I haven't get any output, right? Now, if I would like this resistor to start producing outputs, so I'm gonna getting from the clock number what? Huh? Clock number 5. So this is clock number 1, this is clock number 2, this is clock number 3, this is clock number 4, right? So in cycle 5, there is either that, there is new data like B4, or you are pushing any garbage, right? So if you are pushing any garbage, or you're pushing B4 or B5 or whatever, then SI will be pushing in the D3 B4, in the D2 B3, in the D1 B2, in the D0 B1. And what will be the new output? And output SI SO will be having what? B0 as an output, because no more things. So basically this Q is gonna be holding the B0 in the cycle number what? Cycle number what? 5. Then if you think about it more, in the cycle 6, cycle number 6, the output will be B1. In the cycle 7, output will be B2. In the cycle 8, output will be 3. So that means it took 4 cycles to report the output. Any question? Hello?
Well, so when it's getting pushed through the cycle, then is it becoming like B7?
No, it's basically either that you have data or you're pushing trash, right?
Oh, so it's just like zeros or like nothing?
You can push zeros, whatever, something, right? I'm just giving examples. So this configuration in front of you is suffering from what? It's naive configuration. So, you can think about it as following, right? Pros and cons, right? The only pros we have is what? Simple, less resources to be used, right? It's just it's a wire extended to flip-flop, wire, right?
Yeah.
The cons that the reporting or feeding input, it takes almost number of cycles equal to the depth of the register, right? So 4 cycles because the register are 4 bit, 8 cycle because the register is 8 bit, n cycle because the register is n bit, right? Also, reporting output will be suffering from the sequential behavior, because you are waiting now. Once you already fed the data you want inside the register, you still need to push somehow with valid data or with trash or whatever to get the output later on from the output port, right? That makes sense?
So it's better with less bits.
We're not gonna say better. We're gonna study all of them, and then we can come into, because everything is better, right? SISO, it's serializer. Serializer used in a like infinity application. One of them is actually space application. So every single configuration, it has its own job. Make sense? But if you are a high performance person, then, you know, of course, this is not the right configuration to use. Do you agree?
Yes.
Okay. Now, the second, which is trying to solve the problem that, you know, the serial input has, is called PISO, which is trying to applying parallelism to the input. So in this case, it's called parallel input serial output 4-bit register. Okay, how this will look like, it's really straightforward. It's a naive design. So basically you already have here clock, okay, and we said that's D flip-flop. So we have here DQ, 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 and this is what this is 3 D flip-flop 2 D flip-flop 1 D flip-flop 0. How are we gonna do it? That's not really hard. Why? Because, you know, we're gonna go ahead and, you know, extend input like this, and extend input like that, and extend input like this, and extend input like that. So that's actually parallel input. Do you agree? So you have here D0, D1, D2, or D3. Or, you know, instead of confusing you with the names, I can make it what? I0, I1, I2, I3. How are we gonna get an output?
You connect queues together, or no?
Look. But is it really naive like that? You know, I cannot have two wires here same, right? Do you agree? I mean,
Yeah.
that's two wires going with the same input. That's called hazard, by the way. You're gonna learn this in the 40C100. So of course we need something to make it more fancy. So how are we gonna make it fancy? I can make it fancy for you. What do you think? Much better? So what did I add there? What is this?
Max.
Where one maxes.
Exactly. So this is the max, this is the max, this is the max. Or we can put a combinational circuit. It's up to you. Because max is a combinational circuit, right? You can put git levels. Then, you know, how are we gonna make it work? You will just say here selector. Same selectors, select 0, right? Oh, sorry, select whatever, right? Just write select. So if select equal 0 means, right, input is going to be stored in the register, right? While select equal 1 means start pushing towards the output sequentially to produce output. Make sense? So in that case, if you start thinking about the pros and cons, you will find out that, I saved your time. I filled the 4 cells inside the registers by 4 bits in one shot, in one cycle, right? So this is the pros. So the pros here, 1 cycle to what? To store 4-bit. But there is a cons here. What is the cons? Cons, we need still 4 cycles to produce what? The output. Also complexity.
And resources.
Yeah, complexity level increased. Which is proven that, there is no lunch for free, right? Yes, I fix it, make it 1 cycle, but I pay it and I add extra resources here. So far, so good.
Yeah, can you go back a little bit? Scroll down. No, scroll down.
Yeah.
Huh?
No, like down, like your cons. Yeah.
With you. Anyway, that will be copied already. It's recorded, so no worries, okay? I know my handwriting is really bad, but let's say, I'm left-handed, so that's why. And I never seen any left-handed person, writing really perfectly nice.
Yeah, I'm the same way too. I'm left-handed.
Anyway, so okay, super cool. Now we're gonna move into the 3rd configuration, which is basically what? It's gonna be
PIPO?
where is it?
No, PISO.
PISO, PISO. So we're gonna go in a PISO, and it's under standard. No, we did PISO, right? So no, we
Just
did
did PISO.
We did PISO, right? We just did PISO, yeah. We need the 3rd, right?
SIPO?
Yeah, you didn't do SIPO.
We're gonna make SIPO. So I missed the order, which is fine. So let's go for SIPO. SIPO is a piece of cake, right? Why? I'm not gonna make any more of the register look like flip-flops. I'm gonna make it much better, so easy for me. You know what? Let's make it flip-flop. That's fine. So anyway, you're gonna be like this, like that, like this, like that, right? Cool. It's serial input, right? So that means like this. Right? So GQ, 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 GQ. Now it's a parallel, right? Parallel outputs. Here we're gonna be what? O0, O1, O2, O3. O, that means output, okay? So here is serial input. So pretty much, if you look at it very carefully, you will find out that, it is much simpler than, this one, right? But the input is suffering. You're gonna spend 4 cycles to load the 4 cells accordingly to the data have been sorted from the input, right? Then the output will be boom, 1 shot as an output. So 1 cycle to produce 4-bit output in 1 shot, while 4 cycles consumed on loading 4-bit register with the targeted data. which is opening the door to the pros and cons, right? Pros and cons. What is the pros from your point of view?
One-shot output.
One-shot output, yes. What is the cons?
4-cycle loading.
Yeah, 4 cycle for loading. It is loading process, you're right. What is the last? What is the last configuration now? People.
People. Yeah.
Which is basically what the one we're using for memory. I'm gonna show you now how to build the memory using people. Okay. So now people. How people works? People in general like this. I0, I1, I2, I3, O0, O1, O2, O3. Make sense? DQ. And then you know they're gonna be what's flip-flop, 3 flip-flop, 2 flip-flop, 1 flip-flop. So one shot input, one shot output, right? Pros. One shot input output. Is there any cons?
Complexity.
You think there is no complexity at all? Anyway, tell me, what is the cons?
More wires.
Yeah, that's one of the, yeah, I can consider it one of the things, because there is something that's called fan in, fan out when you go in the chip. But you know what this circuit cannot do what? We can not running sequentially. Right? Which is opening the door on how can you make a configuration. It is parallel in, parallel output, but sometimes it will be sequentially.
Can you explain what running in sequentially means? Like it does one data task at a time, or what?
This is sequential, right? That mean, what does it mean sequential? Every single cycle something is coming, and that will help in the contribution. That's called sequential. You know, this is called what? Parallel.
Oh, you mean like passing data? Okay.
So there is a register. I'm gonna discuss about it for you next time on providing both sequential.
Can you make it sequential if you connect the input and output? Or does it make it never mind. Yeah, I guess you can, because you have an input on each line.
Yeah, you can. But anyway, so far today we learned a very important thing, right? Which is the register. It's what? It's a set of flip-flops sharing the same clock. Do you agree? So that means it's synchronized, right?
Yes.
Normally, you know, such a kind of configuration in front of you, I do it like this. You agree? That's called 4-bit parallel in, parallel out, which is sounds good.
Yes.
Okay. Now I'm gonna show you something very interesting. How can you build something act as a memory? Something act as a memory. So you need to know what is a memory, right? What does it mean, memory?
Stores something? Stores bits?
I'll show you. Memory is the following. A pile of data, which is a table, like a table. And each row, it has a row and it has a depth. Okay? You can consider something is called read file or register file. That's something very famous in computer architecture. But anyway, it's a row and depth, right? The row, it stores something is called word. And the row is literally is what? A register. So for instance, when you guys go buy a memory, right? They tell you what? This memory storing this amount of thing. Like, 4 gig memory, 8 gig memory, 16 gig memory. Did you know what is this? So, and then they will tell you what is the size of the row. Okay? How can we do this? Let's imagine that, our row is a 32-bit. Okay? And our depth is what? 16. So that means how many rows we have in this memory? 16, right? Because depth, that means, I have row 1, row 0, row 1, row 2, boom, 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 up to row 15, right? So that's why 16. So total number of bits this memory is storing is 16 times 32. Do you guys agree? It's going to be 2 power 4 times 2 power 5. That's actually 2 power 9. What is 2 power 9? Somebody can tell me. 512. 512 bit. So this memory is 512 bit. Do you want it to be in byte? What are you going to do? You divide by what? By 8. Because the byte is 8-bit. So in that case, you're going to say 512 divided by 8. That means, 2 power 9 times 2 power minus 3. So you're talking about 2 power 6, which is basically what? 64 bytes. Make sense?
Yes.
So now we learn how the memory calculated the size, right? But how the memory works, we need to make an example. So basically, it's a table, but it's not table isolated from the world, right? It's a table communicating with interfaces, right? So in that case, I have here words up to word, let's say 15 as we did, so we can make a specific design. Okay. Now this table is accepting data from outside. Do you agree? So that means there is something here called what? Data bus. Okay. And it's actually, sometimes we pick data out of the memory and use it somewhere else. That's also called what? Data bus. But this one for storing and this one for what? Pulling data out. So we can call this data underscore n, and we can call this data underscore out. Sounds good? What is the size of this guy? Somebody can tell me. Normally, the memory produce words. So that means the size of this buses, and what is the definition of bus, by the way? Bus is a set of wires. So this bus, it has the size of the word. And we said this word is what? How many bit? 32-bit. Sounds good? Okay. So in that case, this is 32-bit and this is 32-bit. Any questions so far? Hello?
So is it 32 bits? So it's got 32 wires?
32 wires, because they will help me to push data into the whatever word I need. But this is not the end of the design. Still, there is a bunch of stuff need to be added. What stuff need to be added? There is a big research about memory. Huge. We cannot even cover in one or two, 3, 4, 5, 6, 7, 8, 9, 10 lectures. But I'm going to give a simple thing to tie the resistor in your mind with memory. So now, I know how can I push data and I know how can I pull data out, but I have no idea how I'm going to select words inside the memory, right? So in that case, I need what? This gentleman, PTR. You guys use it. What's called? Pointer. So the pointer in the software, if you go in a hardware, it's called what? Address bus. So it has size. So normally when we make a bus, we will make this like backslash like this. So that means, this thing is more than 1 bit. So what is the role of this gentleman from your point of view? It's telling me which row will be hosting this data. Sounds good? Which is opening the door on how many bits this will be covered based on what? Depth. So depth will be used to determine the size of address bus. How is basically log 2 of the depth. Why log 2? We are binary. So we just have what? 0 and 1. So that's why 0 and 1 is 2 bases. So in that case, I said how many words we have in this architecture? We said what? From the previous. Was what?
16.
16. So in that case, it's going to be what? Log 2 of 16s. How many bit will be? 4 bit. So in that case, I can literally go ahead and write what? This is what? 4 bit. This pointer was amazing enough to help me to feed the memory with data. Do you guys agree?
Yep.
Now, I don't have the mechanism for picking data out of the memory, right? So I need another what? Another
pointer.
Or, I mean, it depends on the memory architecture because, memory can be working with one pointer, right? That's called single address bus memory architecture. So that's a long story, but we can think about it later. But anyway, now we already have another pointer, and of course the same size of that pointer should be aligned with the same size of the pointer for what? Writing. So that's gonna be also 4-bit address bus. We're not gonna call it pointer. We're gonna call it address bus because we are in computer architecture or the digital logic visit. We are not in software now. So anyway, we need to name it so it's gonna be easy for us. So we call this data in and we call this what? Data out. And we call this what? We can call this address, right? And we call this what? Address what? Read. Now we have a memory, but how can we build it in reality with whatever we learn from the combinational circuit and the what's called and the sequential circuit registers. So the best candidates will help me to build this memory. As you can see, there is no sequential movement, right? So it's actually used what? People. So every single word will be a people. So in that case, I need what? I need a resistor. I need another resistor. I need another resistor. And I need another resistor. 1, 2, 3, 4, 5, 6, 7, 8, up to 15. You guys agree? How many resistors do we have in front of us? 16. So gonna be here R1, resistor number 1, R2, R3, R4, R5, R6, R7, R8, R15. And we know every single resistor is what? Huh? People. Do you guys agree? And we know also this resistor, this memory can be what? To be synchronized. So in that case, I need to go ahead and make what? Clock like this. So I'm gonna extend my wire like that. It's gonna be clocked like this. So first of all, it is people or not? People, right? So in that case, I can use a different color to define my input. So here is my first input. And it's what is the size of the input? Somebody can tell me, what is the size of the input? Hello?
4-bit?
32-bit?
Yes. 32.
So each register can store 32-bit?
Yeah, it's a word, right? Everybody agree about that? So this is PI, right? Parallel input. Also, we have parallel what?
Output.
Exactly. So we can make it like this.
Where does the pointer get connected?
We're gonna see now everything. Just wait and you will be surprised. Okay. Okay, now we need to start using our knowledge for the feeding back and forth, right? So the best ways to do it, what is to make this registered controlled with enable, and we don't need to describe that because we already described it before, right? We know enable, right? So what is the rule of enable? The existence of the enable will do what?
Activate it?
Come on, the existence of enable will do what? Will activate it. That means, the register will start moving the input to the output. Do you guys agree? So I'm gonna add now extra wire and I will call it was enable. Sounds good? So this EN0, EN1, EN2, EN3 up to EN what? 15. And the top of that, we have one input data bus here, right? Do you guys agree? But I see here in front of me 16 inputs. So in that case, what I can do, I can actually go ahead and make a common wire like this, saying those guys are connected like this to each other. That would be our what? Data in, and it's 62-bit. Somebody can tell me roughly what exactly I'm gonna add here to control the enable from whatever we learn from the combinational circuit.
A multiplexer.
No. Decoder. So if you have a decoder here, that decoder will produce how many outputs? 16. So this decode is a decoder, and it's actually 4 16s. So that means how many inputs will be connected? 4. And guess what those are? The address bus. Let's say, right? Let's have here assumption, right? Address bus equals 0. That means 0 0 0 0 0 0 0 0. What happened when the decoder address bus equals 0? Who actually got activated? This one.
And 0.
Yes. Then whatever inputs here going where? Inside who? R1. But the rest, because they are not activated, they will never be connected. You agree? So the data will be moving like that. Do you guys agree? So we succeed on building the mechanism that will allow us to move data using decoder, controlling the registers with enable that will be feeding the whatever register I want based on the value here. It will be written in the 4 bits. So if, for instance, if I wrote here instead of 0 0 0 whatever, I'm gonna write let's write 7, right? 1 1 1 0. So 7, right? So now I'm gonna go in 7. So where is 7? 7 is gonna be here, right? So basically that's where it will be activated, which means same color. So I will use the same color. So that means this will go like this, and the data will be written here. The rest are not enabled, so that's why they're not working. So my question: do you have any questions so far regarding this part? Hello?
No.
Sounds fun? Now let's work on the second part, which is basically what? A reporting output. But I have 32 outputs. What I'm gonna do? Then whatever you mentioned, it was the correct for the other side, which is multiplexer. So that multiplexer will be like this. So gonna be a 32 multiplexers. Each multiplexer will be what? It will be what? Mach 16.1. 32 times. Why? Because this is going like this, going like that, going like this, going like this, like this. And the selector for this multiplexer will be what? Log 2 of 16, which is gonna be what? 4-bit. So in that case, this one is what, from your point of view, is the address bus read.
Yeah.
Do you guys agree? So in front of you, this whole design is equivalent to this. What did we use? We learned today registers. So let me summarize. So basically, we talked today about the beginning of the registers. We start talking about what is registers. It's a set of flip-flops are sharing the same clock, so that means they are synchronized. We said the right candidate to be used for building a register is the D flip-flop. And then we came into the point of how can we communicate with the input and output, and we call this configuration. We define the configuration as serial input, parallel output, serial input, serial output. We call it CISO, or serial input, parallel output, which is a CIPO or whatever, and parallel input, serial output, which is PISO, and then with the parallel input, parallel output, which PIPO. We defined the pros and cons for each one, and we said all of them are still valid. It can be used for different applications. We picked one of them, which is basically PIPO, and we built something acting as a memory with associated combinational circuit, helping us to define that by defining the size of the memory in the beginning by the depth and the number of words, which is the size of the number of flip-flops per element on the row. And then after that, we made a calculation offhand. We figure out how can we do it in general. Then we defined the ports, as you can see, which is associated for reading and writing. And then we build a very nice memory, as you can see, with a combinational circuit multiplexer for reporting output, while the decoder will be controlling the flow of the inputs going into the registers, as you can see in the architecture. Do you have any question?
Nope.
Perfect. Hopefully, you guys are enjoying the course, and hopefully by next time I will bring you I will post the grade for the midterm number 2. So we can stop here for today. I don't want to overwhelm you with too much stuff, so you can take some rest or break before we will move to the next lecture. So next time we're gonna continue with our discussion about the registers, as you can see, and we're gonna talk about what shifting and rotating, and how can also you do, instead of sequential, you can do with combinational circuit, which is called parallel shifter. After we finish this, I will head back into the sequential or the sequence detectors, and then we can move maybe to a little bit of the building ALU, and then we can talk about introductory for Verilog. Sounds good?
Yep. Sounds
okay,
good.
so it was my pleasure to talk to you today. I wish you the best of the luck, and I wish you the best of the rest of the day, and I will see you on Wednesday. God bless all of you. Thank you.
Have a good one.
You too. Thank you. Bye-bye.
Thank you, Professor.
Thank you. Bye.